exponential growth, exponential decay, and radioactive decay, which is half-life. That is very specifically half-life. Okay. So, exponential growth. The A is our final amount. The P is, if we were talking money, we did this the other day, P was principal. P is our starting amount. How much did we have to begin with? A is how much do we end with? R is the growth rate, and X is time. Difference between exponential growth and exponential decay is you're subtracting the growth rate instead of adding the growth rate. You're streaking at a particular amount. Okay? And on the half-life, it's a little hard to see on your printed copy. Okay, but this is X over H. It's hard to read. The X is kind of covered up a little bit by the Y on your paper, on your note paper. It's X over H. X is the time period. H is the length of the half-life. So, for example, we'll be doing a carbon-14 problem, and carbon-14 has a particular half-life of a certain amount of time. That's what the H is what the half-life is for that particular isotope. Some things have half-lives measured in nanoseconds. Some radioactive things have half-lives measured in eons. Okay? It just depends on what you're talking about, how long that half-life is. And we do understand what half-life is, right? How long it takes for half of that to decay, how long it takes for half of that to decay, right? Okay. Which means that there's always some radioactivity. Eventually it becomes unmeasurable and becomes safe, so it doesn't do anything. That's the problem. Now, so the first one's a little trickier because it's not quite exactly one of those particular models. Fruit fly population triples every day. It does not have a particular growth rate or percentage. It does not grow by 10%. It does not grow by 20%. It triples every day. So this one's a little bit different in how you set it up, but it's fairly the same. It triples every day. Today it's at 200. That's our P. That's what we're starting with. So I have 200 times its growth rate is 3. It triples every day. So it's 3 to whatever the X number of days is. Now in this case, how many will there be at the end of the week? So X would be 7. Okay, no. I said this one's a little different. If it says that it doubles each day or triples each day or quadruples every hour, okay, this is the model you use for that. It's not exactly the same exponential growth. This is the 1 plus R combined into 1. If it doubles every day, it would be 2 times that. If it triples every day, it's 3 times that. It's 3 to whatever that power is, however many days or whatever the time unit is. Let's say it's something that doubles every hour. That would be 2 to the T, and T would be measured in hours. Okay. This is actually very similar to the half-life problem, only instead of half each time, it's 3 times each time. So this model actually follows this one more closely than it does the other two. But it's a key to the problem. It tells me it triples every day. If it's a whole number that it changes by every day, if it's not a percentage, then that's what you're going to be using it as. So if it doubles every day, that would be 2. It's half each day or half each time period. So this is why it's 0.5. This is 3 times each time period. So it works that way. And then literally you plug that into your calculator, and at the end of the week, you have 437,400 freaking fruit flies. I remember I did not have the class, but many of my friends had the class when I was in going to Humboldt, it's Zoology 1. Zoology 1, actually, I think it was Zoology 100, like Zoology 1. It was the introduction to zoology. Everybody who was a wildlife management or natural resources or a fisheries person had to take a class. And one of the labs was the fruit fly lab. For 24 hours, you and your partner had to count how many fruit flies were in your petri dish over every 15 minutes for a 24-hour period. Literally, everybody's sleeping in the hallways. In 15 minutes, alarm goes up. Everybody gets up and goes counts. And you had to keep that count. I didn't have to do that. Thank you. And yes, this is like the kind of growth rate they will have. Eventually, they will meet the pre-population, but hey. Okay. Filtering tap water. Okay. Filtering tap water removes 30% each time. Is this a growth or decay? Decay. Decay. And what is my decay rate? 30%, which would be 0.3. Okay. How many times would you have to filter it to ensure that 95% of the impurities were removed? What is my final amount that I want to end with? I want to end with 5%. Not 95%. I want to remove 95%. So if I start with 1 and remove 95%, how much do I have left? I have 5% left with. So my ending amount is 5%. So that means I will be using the exponential decay. So that means 0.05, sorry. 0.05 is equal to 1 minus 0.03. Sorry, 0.3. 30%, my bad. To the X or T for time. How many times do I have to do it? Then you solve for that. No. Actually, I think it does. We'll find out in a minute. I'm trying to remember if it does or not. 1 minus 0.3 is 0.7t. Now, how do we solve this problem when we have an exponential and two numbers that we cannot make the same base? Take the log of both sides. Natural log, if you please. Take the natural log of both sides. Bring the t down out in front. So I get t times the natural log of 0.7. Equals the natural log of 0.05. Divide both sides by 0.7, and I get t equals the natural log of 0.05 divided by the natural log of 0.7. And t is equal to 8.39. However, what am I doing? I'm pouring water through a filter. Can I pour the water through the filter 8.39 times? Oh, yeah. No, I can't. So how many times am I going to pour it through? 9 times, because 8 won't be enough, so I have to do it 9 times. So how many times will I have to do it? I'll have to do it 9 times. 9 times. 9 times.
How old is the mummy that's 0.6? Exactly. How do you know when to use a natural log?
Always use natural logs when you take the logs both sides.
No.
That's going to be standard in here. You could use log base 10. It doesn't matter. You get the same answer. But get in the habit of using natural logs every time. Doesn't matter the base. When you do this, when you take the log of both sides, it does not matter the base of the logarithm you're doing to both sides. You can do log base 10, you can do the natural log. We are going to do the natural log as often as possible because that's where you want to be headed. You want to get practice using the natural log instead of using log base 10. Okay, if you forget on the test or on your calculator and use log base 10, you'll be fine. You'll still get the same answer. You'll still get the same numeric answer. It just you want to get the habit of using natural logs because it's one of those things. We're changing from log base 10 to natural log because we're using more exponentials using E, what you're going to be doing, get comfortable with it. That's really what I'm looking at. Try to get comfortable with it. Okay. The half-life of carbon-14 is 5,730 years. Woo! How old is a mummy that lost 40% of its carbon-14? Okay, so this is the half-life formula. Okay. If it's lost 40%, how much does it still have? 60%. So that would mean 0.6 is equal to the half-life. And what do we start with? If we have 0.6, we start with 1. Because we want 60%, right? So we start with an amount of 1, whatever we began with. Look at it as being, if we're talking percentages, you start with 1. If it doesn't give percentages but actual numbers, it will give you what you actually start with and what you're actually finishing with. But we're talking percentages, you have 1 on one side and you have the 60% on the other side, the part of the whole. And the 1 really won't make any difference in your calculations. You have 0.5, and it says, how long will it take? How many years? Divided by 5,730, because that's the half-life. So in 5,730 years, when t is that, what do I have with my exponent? I'm going to have 1, which means I've taken a half away. Does that make sense? So that's how it works. That's why it's the time period divided by the half-life, because this is how long it takes to get halfway. So if we have that exact amount of time, half will be gone. If we have double that, then 1/4 will be left. If we have half of that, then 12.5% will still be left. That's what I'm saying. Okay. So solve for t. The 1 I can ignore, right? I can just ignore the 1 that doesn't mean anything. So what do I do now? I have 0.6 equals 0.5 to some power. I take the natural log of both sides. Okay. Bring the power down out in front. So I get t over 5,730 times the natural log of 0.5 is equal to the natural log of 0.6. Divide both sides by the natural log of 0.5 and multiply both sides by 5730. So I get t equals the natural log, equals 5730 natural log of 0.6 divided by the natural log of 0.5. And if you're working this out at one part at a time, you will have a negative, not for your final answer, but you will have a negative on the way because the natural logs, the numbers less than 1 are negative. But you have a negative and a negative that'll cancel out. And so this mummy is 4,220 years, 220.8 years old, give or take. Give or take. It is actually fairly accurate. Carbon dating is actually really, really, really pretty accurate. Okay, one of the things I love about California is that we have the largest living thing in the world in the state of California. We have the tallest living thing in the world in the state of California. We have the oldest living things in the state of California. Okay, the largest living one are the Sequoia redwoods, and we have the largest one there is down south, actually south of Yosemite. The tallest one are the coastal redwoods. And the tallest one is up in, I think it's Richardson Grove, up in Northern California, Humboldt County. The oldest living tree thing in the world is the Medusa tree. The Medusa tree is at the very southern tip of the Sierras. Actually, it's the White Horse Mountains. It is a bristlecone pine. It is well over 3,000 years old. It is older than the freaking pyramids. No, it's not. I'm probably about as tall as it is. It grows very, very, very slow. It is an extremely dry environment. It's on the edge. It's on the mountain edge of the Mojave Desert, so there's like almost no moisture that gets there. It grows extremely slow. It's probably about that big around, and it's like,
So how did we know it was so old?
count the rings. There was one that was older that was in Utah, and some guy cut it down with a chainsaw. Now he did not know what it was.
Yeah.
He did not know. He was out cutting firewood. He did not know what it was. He did not know what he did until later, and he feels like crap for it. He does not know. The Medusa tree has been identified as the oldest living creature on the planet, and there are maybe a dozen people that know which exact tree it is of the ones that are in that grove. And the grove is highly protected, so some idiot doesn't walk up there and try to film themselves and post it on Facebook that they're killing the oldest thing, because we have idiots in this world that would do that.
It's 4,800.
4,800 years old. And what they've done is they've taken limbs and branches that were nearby and carbon dated them and counted the rings on the living ones. They knew exactly how old the branches were when they fell by matching the rings, and they carbon dated it. And the carbon dating actually was pretty darn close to what it actually was, because they can count the rings and figure out exactly when that particular tree had fallen, comparing it to the actual living ones. Yeah, that's really cool. Okay, the population of Mexico was 67.4 million in 1980. It's an increase of approximately 2.6 yearly. Estimate the population in 2020. Okay, this is growth, right? So we're trying to find the final population. So we're trying to find the final amount. This is actually probably the easiest problem. No, second easiest one. Okay, how many people are we starting with? 67.4 million. So our answers will be in millions. Do not put a bunch of extra zeros on there. It's not worth it. 1 plus what?
Plus 0.026.
2. What's our time period?
40 years.
40 years, because it's 0 is 1980. We're going to 2020. I don't want to hear that. Okay. Plug it in your calculator and figure it out. That's at this point, that's what it is. Take 1.026 to the 40th power, multiply that by 67.4. 188 point, I'd call it 2 million, rounding it off. Because you can only round it off. You can't go more accurate than that, because your original count was a bit more accurate than that. Take significant digits in science. Questions? So this one isn't too bad. That one's a plug it in. Most of these aren't too bad. The trick is knowing which model to use. Okay, now we have logistical models. Okay. So logistical models, P of T, population at time T. C is the carrying capacity. Carrying capacity, sorry. A is a numerical value based upon the individual thing that you're talking about. There's not really a good name for it. It kind of depends on what you're doing. It's something you figure out why you're doing that statistical collection of data at the time. B, that is the growth rate. Okay.
T is done.
And T is fine.
Wait, so A is just like
A is an odd one. A is a particular value. It's hard to determine. You will never have to find that. You'll be given that value to begin with. Okay, of what that number is. I've done it a few times in a couple of classes that I've had a long time ago. I don't remember the exact name for that. Let's put it that way. But what it is, it's a particular value that applies only for that particular situation you're working with. It's not going to always be that same value that we have here. Depends on what you're talking about. And this is a good logistical model for any population of anything. There are carrying capacities, there are growth rates. There's a lot more that goes into it in the long run. This is a fairly simplified one. If you were doing population counts and such and projections, this would give you a good start. Yeah, this will give you a good start. There's a lot more you can get into it to make adjustments. So we have a problem here. After environmentalists move 6 endangered bald eagles to a controlled environment, the population grows according to the model. P of T is equal to 500 over 1 plus 82.33 e to the negative 0.162 t, where t is in years. And t is always defined what units we're talking about: years, days, weeks, months. It all depends upon what you're dealing with. Most animal populations would be years. Some insects would be days, depending upon the lifespan of that particular insect. Okay. What is the carrying capacity of the environment? 500. That's what it's given us. It's 500. What could determine the carrying capacity? What can determine that? How much space there is, amount of food, amount of predators. Bald eagles generally don't have a lot of predators, but other ones might. You know, competition for food. Yeah. Lots of different things. Everybody has this majestic bald eagle. And bald eagles, don't get me wrong, are extremely majestic, but they eat crap. Okay. So our carrying capacity is 500. Now, mathematically, let's take a look at the problem here mathematically. So if we look at what we have going on here, we have 1 plus 82.833. So the 1 is the 1. As time gets bigger, as time gets larger, I get e to a larger and larger negative value. When I'm raising something to a negative value, that's the same as 1 over that value to the positive 0.162t. As t gets much, much larger, 20 years, 30 years, 40 years, 50 years, 100 years, what's happening to this number on the bottom? This is getting really big. What's happening to this whole thing? It's getting really, 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 really small, getting close to 0. And 83 times something that's getting really, 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 really close to 0 eventually becomes 0. So what do I have? 500 over 1 plus 0, which is 500. So mathematically, you can see where the 500 works is what it's going to be over a long period of time.
holy limit.
Okay. What is the growth rate of the bald eagle?
Half, like 0.16%. If I put negative 0.162.
No, because it's always minus P of T. If you look closely at your thing, it's minus P of T. So the growth rate is 16.2%.
A year.
Yeah, that's not bad actually for something that they don't have a whole lot of babies that have to survive. They only have 1 or 2 at a time. So it's barely over replacement level. What is the population after 3 years?
9.
Okay.
They are
500, 1 plus 82.33 e to the negative 0.162 times 3, which gives you approximately 9.68, which is approximately 10 birds.
Wait. Holy round. I feel like when you round down,
Yeah, you can round up or round down. It really doesn't matter because it's not going to be exact anyways. It's about 10 birds. It's more than 9.5, which is closer to 10 than 9, right? Because it's not like it's an exact value. You hope that's what you have. You'd be looking at a few more than that. Okay. Now it says, when will the population be 300? Graph it, and I did. Okay. So I graphed it, and this is the logistical model. Look what happens. It starts out, almost nothing. It's at like 1 right here. Okay. And then it starts growing really fast, and then levels off 500 because as we start getting larger and larger values, remember the denominator becomes really, really small. It becomes close to 1. So we get that. And I actually graphed 300 so I can find the point of intersection. Okay. So 300 birds in 29.7 years, approximately. Something like that. Okay, how long will it take the population to reach half the carrying capacity? What's the half the carrying capacity? 250. So that means I want to know 250 equals 500 over 1 plus 8, 2.33 to the negative 0.162 t, and I want to solve for t. Okay, actually, this is kind of cool. There's a couple of ways to think about doing this. Now, I have on one side a fraction. What do I have implied on the other side?
Fraction.
I also have an implied fraction on the other side.
Wow.
Which means that we have a proportion. Now, when you solved proportions in the past, one of the ways you did this was you cross multiplied. But I'm going to show you something else that's even cooler. Whenever you have a proportion, there's all kinds of neat things that you can do. One of them, you can just flip them both over. You can do that. You can just take whatever proportion you have, flip them both over. That'll put your variable in the numerator. That's one way to deal with it, and it's not what I'm going to do. The other thing you can do is you can swap either the means or the extremes, which means that I can swap these two numbers, which means I get 1 plus 8 to 2.33 to the negative 0.162 t is equal to 500 over 250. You can do that. It's one of the really cool things you can do is you can swap the means and extremes. So you can swap either one of the diagonals, either these two or these two. It will still be equal. It'll still be equal, and that's what I did. Yes? Oh, I'm sorry. I dropped it on accident. My bad. My bad. Thank you. Thank you. Did I drop it here too? Oh my God, I dropped it here too. My bad. I'm sorry. My bad. So what's 500 divided by 250? 2.
Oh my gosh, it would be 1.
Okay. Subtract 1 from both sides, and you get 2.33 e to the negative 0.162 t is equal to 1. Divide both sides by 8.233. E to the negative 0.162 t is equal to 1 over 82.33. And please do not try to simplify that yet. Just don't do anything until you have to. Now there's a couple of things I could do. I could take the log of both sides, or I could loop it either way. Bless you.
Bless you.
Okay. If I take the log of both sides, the natural log of e to some power is just that power anyways. So I get the power equal to the natural log of that. So that means I have negative 0.162t is equal to the natural log of 1 over 82.33.
That's the one over.
T equals the natural log, and this is all one thing, 82.33, all divided by negative 0.162. And you're thinking, oh, I've got a negative in there. Yeah, but the natural log of a number smaller than 1 is also negative. So you'll get negative over negative, so you will get positive time.
27.2. I don't know what this is. No, I
Say questions.
They're all in my minutes.
We've got like 3 minutes. Okay, so once again, proportions. A over B is equal to C over D. Proportion. A review. If I have this original value, I also have AD equals BC. Cross multiplying, that's how you solve proportions, right? Multiply the means and extremes. And the means are these diagonals and the extremes are those diagonals, I think. I can never remember, all I know is the means are one pair of diagonals and the extremes are the other pair of diagonals. You can flip the whole thing over. B over A is equal to D over C. So if you have a proportion, you can flip it over. Sometimes you're going to want to do that to solve them. Make one-sided fraction like what I did, flipping both over. That's often a very useful thing to do. Once again, you can swap. D over B is equal to C over A. And you can swap the other twos. A over C is equal to B over D. If you're given this, all of those are all true. It's extremely useful for solving problems because you don't always want to cross multiply. Sometimes just flipping them over will actually be the easiest thing to do. Okay, it's an extremely useful tool for solving some very difficult problems sometimes, and being able to use those, remembering those. Okay.